Now, there are a couple of different aspects related to error handling and debugging that we'll also look at in a little bit more detail. Once again, these are ideas that benefit from the understanding of design patterns. Right? The first question, what do we mean by an error in the first place, right? Any kind of wrong behavior in a program or a system, right? By wrong, it could just be that it's unexpected, it could be that it's undefined, right? It may not be as simple as a calculator that says 2 plus 2 is equal to 5. It could be some other kind of behavior where you do not expect a system to perform a certain kind of behavior. So what's the problem, right, with errors happening? Embedded software typically is long running, meaning that you have embedded systems which once you switch them on are expected to pretty much just work and work and work, and restarting or resetting the system repeatedly or often or even at all could be difficult. There can be safety critical applications including things like nuclear power plant control and so on, where essentially resetting the system is not an option, right? You don't have a choice, you have to have the system working correctly at all times. Okay? And one of the things where error handling in the context of embedded systems is different than in traditional software systems is the resource constraints. You simply do not have enough computational power or memory to waste on wrong behavior. Okay? Now, there are a few sort of highly desirable characteristics of error handling systems. One of them is what's called graceful recovery, right? I mean, if an error happens, how do you sort of recover from it and still keep the system going in some way, right? The overall user experience, what happens to the user who is actually trying to use a system, right, when an error does occur, is a key consideration out here. And not to mention that debugging and maintenance should be as easy as possible. You have to sort of design assuming that certain errors or errors could happen. Try and minimize them, of course, but if they do happen, how easy is it to debug and maintain the system and possibly fix it? There are you can broadly classify errors into these three different types. Compile time errors are things like syntax errors, type mismatches. Always preferable because you can catch them early, and especially in embedded systems, this is a key observation, right? They typically have a long runtime. You compile once, you put it onto the system, and then you forget about it. It's just running all the time. So the difference between the amount of time spent in compilation versus in actually running is huge in embedded systems, right? So if you can catch something at compilation time, it's always preferable. Now, what that means also is that if you end up developing your code in certain kinds of interpreted languages like MicroPython or other kinds of things that are literally or embedded JavaScript or something like that, where there is a certain interpretation component at runtime, right? You could even end up with a scenario where certain fairly simple errors don't even occur until the system has been running for a while, right? Whereas certain kinds of compilers, a C compiler or certain languages such as Rust, which are explicitly trying to catch as many bugs early as possible, especially memory related bugs, right? Those kind of things would benefit because they would avoid a certain class of bugs from ever happening at runtime just by making sure at compilation time that certain scenarios cannot arise. Now, ideally, yes, you catch your errors at compile time, but what if you don't? Then you go to runtime. The kind of problems that you could encounter there, a lot of them are memory related, right? When you're talking about the software, it's largely memory related. It could be buffer overflows, you could have null pointer problems and so on, right? You could also have hardware errors, but that's actually a hardware failure. It's not always obvious that you can fix those in software. Although the whole idea of sort of detecting a fault in hardware or detecting an error that arose due to hardware and recovering from the system without necessarily losing the entire system is also a very important part of fault tolerant design, right? Right now we are talking more about the software related errors themselves. And finally, you could also have logical errors. These are actual program logic, right? The functionality itself is wrong. It is quite possible that it occurs in some very hard to reach state of the system, and therefore is not caught either at compilation or even during the initial testing phases, right? It might be that the system goes into deadlock under some specific kinds of conditions. There are things like race conditions that can happen because of asynchronous events and the order in which they occur. All of that can lead to certain kinds of errors. So now how do we handle such errors, right? And a few different sort of suggestions on error handling in general. One very common thing is the idea of an error return code, right? Every function in general, ideally of course it returns a value that was actually computed in the function. However, in a lot of cases what you want the function to do is to sort of perform something with side effects. In other words, you are updating something in memory, you are printing something out, sending data over a network. Okay, if that is the case, then this value that the function is supposed to return could be used by you as a return code, right? A common convention in C is basically to say that if something returns 0, then it's basically there was no error, right? Any non-zero value that gets returned from a function call is typically considered an error, right? So it ties in with the idea of modular programming where you have function calls and you have return types. C unfortunately does not really give you the ability to return complicated data types. There are other languages that actually make some of these things, you can actually write code in such a way that the error return type and the actual return type can be sort of combined together and can give you some very interesting properties in terms of how you write the code. But we are not getting into those details right now. From the point of view of a language like C, what you can do is return a simple error code, a number. If it's non-zero, it indicates some kind of an error. What this means is that once the function returns, whoever called this function has to check that return value and decide, okay, was it okay, or do I need to actually go in there and check something based on this, right? And in certain circumstances, you might find that, okay, if the read sensor failed, whoever called read sensor in turn has to propagate that error upwards, maybe all the way up to the GUI that's actually going to display an error somewhere for the user to see. It's very simple to implement, also involves very low overhead. However, it can be ignored. The number of times that we write C code where we file star fp and then fp is equal to fopen, right? File open function call, and then we don't really check whether the result was actually null or not, right? It can happen, it happens all the time. It shouldn't ideally be done, but if it does, the point is that the error return code can be ignored. It can also lead to clutter, meaning that you have a lot of different check conditions that you need to perform in order to see what happened. Was there an error? How do I respond to this, and so on. Another alternative is to have some kind of global variable which acts as a flag, right? So you have some kind of an error flag which is defined somewhere in your global variable space, and you have functions that basically are able to set the error flag, right? And in other places you could basically check the error condition and say, okay, if there was an error flag, then basically don't do any work. So your main loop, for example, could just have one thing which says every time before getting into the loop, check whether there are any errors, and if so, do behave in a different way, right? Now the problem of course is there could be multiple different people who are trying to write to that particular error flag, which can lead to what are called race conditions. Maybe one of them sets the error flag to 0, another one sets it to 1, and depending on the order in which these happened, the system might not even realize that something went wrong. Okay, so error flags are common simply because they are easy to check anywhere in code, which means that for embedded systems which don't have a lot of memory space, right, it makes your code a little bit simpler and probably easier to implement. Assertions are actually something which ideally, well, this is not exactly compile time, but it is just something which basically checks whether a particular condition is satisfied or not, right? You have a concept of something called invariants when you are writing programs, which basically say that this condition must always be satisfied, right? It could be that let's say that you're measuring a temperature, and you can straight away say that this temperature should never be negative, perhaps because it's on the Kelvin scale, right? And you could essentially have a check, an assertion that basically says if this value ever becomes negative, it means something went fundamentally wrong, right? It can help in terms of catching errors early because it's fairly simple to put in there, and from a compiler point of view, all it does is it pretty much just makes the program crash at the point where the assertion fails. However, that also means that you don't really want to put it in production code. Production code meaning that once you are actually deploying it out in the field, because if a program just crashes, it doesn't matter what the error message was. As far as the end user is concerned, they can't be sitting there, debugging and finding out what's wrong with the system. Okay? There is also the notion of exceptions, which, as we have seen, are related to the idea of interrupts, but are synchronous, things that basically come in software generated, right? So you could actually say, okay, actually create a communication exception, perhaps because your communication channel didn't work, right? So you're not able to print something out, but you throw this exception, and maybe there's a fallback communication channel or some other logging channel or something simply to make an LED turn on, right, which basically makes it work. Now, exceptions are not always available. For example, C by itself does not have a notion of exceptions, but C++ does, right? So depending on the kind of language and how you are developing things, you might find that exceptions are a good way to handle certain kinds of errors, but they are in general more complex to implement, and they also have higher overhead than the other methods that we have looked at. There are many other kinds of techniques. We have already discussed briefly the idea behind watchdog timers. There could be certain things like fail-safe modes. There could be redundancy, where we basically have multiple different things checking, and one of them could, or rather maybe you could, for example, have 3 different systems performing a computation, and if one of them goes wrong, it still doesn't matter, the majority will win. This happens, for example, in space related applications where there is actually a physical chance of hardware errors giving problems, and you don't want to get stuck because of that. For communication, you can have error correcting codes. Self-tests and diagnostics are used a lot, especially at, when a system starts up and boots up initially, right? The point is that there are many different ways by which errors can be handled. Ideally, you want to prevent the errors from happening, or you want to catch them as early as possible at compilation time. If they happen at runtime, you need to have some way by which they can be handled in a way that is as easy as possible for the user to respond to. So there are many strategies that you can use. We can basically classify errors as either recoverable or non-recoverable errors, right? System level or module level. What does that mean? Recoverable means that, okay, something went wrong, but the system continues to operate. Non-recoverable is what we would normally call a crash, right? The system just stops working, and hopefully if you restart it, it works. You could have system level versus module level. Maybe your Wi-Fi chip alone stops working, whereas the rest of the computer continues to work. Just turning it off and on hopefully will bring it back up. Now that's as far as the types of errors that you have. But what do you do with the errors? How do you report them, right? You might want to have some kind of logging mechanism which actually records that these kind of errors occurred. If you are able to communicate with the outside world, then yes, you should ideally send out a message saying that something went wrong. In certain cases, you might not really have that ability. You might only be able to turn on a light, right, which basically says, hey, something went wrong. Okay. And finally comes the recovery mechanism itself. Okay. One could be as simple as report and proceed. So that's basically for recoverable errors in the first place, right? You might have what is called graceful degradation. Let's say that your Wi-Fi chip stopped working. The rest of your system continues to operate until you decide what to do, right? Are you able to restart the Wi-Fi alone without bringing down the entire system? If that doesn't work, maybe you have to just restart the entire OS itself, right? And of course, in a lot of cases, it turns out that the recovery mechanism finally involves some kind of a system level reset, either a partial reset of only the affected parts or a complete shutdown and restart of the entire module. In many embedded systems, As far as possible, you do not want to have full system resets, but there can be scenarios where you can't escape from it, and that's the only option that you have. So having looked at all of these other software design patterns, we are going to look very briefly at the notion of debugging. We will be looking into debugging in more detail in the context of actually the kind of extra hardware assistance that you can get for debugging. At this point, we are only looking at it from a high level point of view. Now, this is an interesting picture. It's basically literally the first reported use of the word computer bug, right? This was a logbook by Admiral Grace Hopper, who has been credited with at least sort of popularizing the term bug. Although this was literally a bug that was found inside a computer. In this case, it's a moth, right, which had got into one of the vacuum tubes and or a relay, and was basically preventing the system from working properly. So as you can see, it basically says it's the first actual case of a bug being found, right? But that apart, what is a bug in general, and especially a bug in the context of an embedded system? Now, as we sort of know, bugs are errors, yes. They could also be some kind of wrong behavior. So in general, whatever we classified as an error earlier is faulty behavior, right? Things that you don't expect the system to do. In general, any bug is bad news, right? But in the case of embedded systems, there are some features that make the presence of bugs much worse. Those include the fact that you have very limited visibility into the system state, right? It's very difficult to add a lot of logging and debugging information in embedded systems, right? There are many systems that have a real-time nature, right, which means that you can actually end up with some kind of transient bugs, things that occur once and then next time when you are trying to reproduce the bug, you are not able to get that same behavior, right? And you could have hardware-software interaction issues, right? So many of these of course do come up in general software, but they are made much worse in embedded systems because of the fact that you are also dealing with a very constrained system, limited computing power, limited memory resources, limited communication abilities, and so on. So what are the strategies, right? What kind of things can we use in order to do some kind of debugging? This simplest is some kind of a status indicator, right? And we have this LEDs. So one of the reasons why LEDs are so popular in the context of embedded systems is because they are the simplest means of communicating information from the system to the user, right? You literally don't even have the luxury of a print or printf statement to actually send a message across. All that you can do is have some kind of a status LED, and very often we are used to this. If one particular LED glows red, then it indicates something went wrong. Whereas the convention is typically if something else is glowing green, then that's good news. It means everything is working as expected. These are conventions which make it easy to just at a glance tell whether things are working as they should. Unfortunately, it also means that there is very limited expressivity over here, right? You can't really convey a whole lot of information using one or even a few LEDs. Now this is an example from I believe the 70s or so, right? The Digital Equipment Corporation computer, and you can see that there are a whole lot of LEDs put out over here, which are all in some sense status LEDs. They are indicating something about the behavior of the system. Now that was required because those kind of systems had very limited kind of other communication abilities, or at least it was expensive to add anything more than lights over there. So whatever debugging you can do by sort of interpreting the different lights that you have on the system, you do that first, and then you figure out if there is something else you need to dig deeper into inside the actual system. Now printf based debugging, right? What exactly does printf based debugging mean? It basically means that you put in printf commands or function calls, right, at various points inside your code, and you could in fact take a function that you have written and break it down into steps, right? You do some amount of work and send a printf saying okay, this much work was finished. Do some more work and then put another printf saying okay, finished some more work, right? Now, why would you do this? It's logging, right? It just basically gives the person who is writing and monitoring the code some information about what has happened so far, right? And it's a very simple and powerful way of debugging. Those of you who have booted Linux systems from scratch would know that there are a whole lot of messages, the kernel messages that scroll past before you actually start seeing the system booting, right? And the reason that's done is because at the time that the system is starting up, you have very limited access. You cannot, for example, draw things on the screen. You can just pretty much print text onto the console or onto a serial port. So those kind of debug information, or just any useful information, tells you how far along the booting process the system has come. Once again, the reason why it's important is because you have very limited communication facilities at that point. You don't have a mechanism whereby you can have a pop-up screen coming, pop-up window coming on your screen telling you something went wrong, because you don't have a screen yet, you don't have graphics on the screen. Okay, so this kind of printf based debugging is very useful. It is brute force, right? It just literally tells you where you are in your code, but it does require the presence of a communication channel, and interestingly enough, it can actually affect the timing of how things work in practice, right? And the reason why this works is a printf, for example, could be sending data out along a UART. Now just think about a UART peripheral operating at 9600 bits per second. It means roughly 1.1 milliseconds per bit that is being transferred, or per bit that's being transferred, which means that for 1 byte of information I take nearly 1 millisecond. Now 1 millisecond in the context of a CPU is actually quite a long time. Even with a 1 megahertz clock, that's nearly 1000, that's about 1000 clock cycles. And if you have a faster CPU like a Raspberry Pi or something like that, it could be hundreds of thousands, possibly even close to millions of clock cycles, right, for the time taken to print one character. If you print an entire string, right, it could basically end up being like millions of clock cycles that have passed in the time that the printf statement completed. What that means is, if there was a bug that was related to events occurring maybe too close to each other, just the fact that there is a printf statement introduced over there could make the bug go away or behave differently, right? The sort of joke term for this is, it's called a Heisenberg, right, based on Heisenberg's uncertainty principle, but of course nothing to do with Heisenberg himself, right? The point is, if you observe it, or you try to measure it, or you try to see what it is, it disappears, right? There are a number of other debugging approaches that we will also be looking at in more detail later. In particular, the whole idea of system level simulators, right? In a lot of scenarios, system level simulation can be cheaper than actually building and testing on real hardware. So you first try to have a complete simulation of everything that you want to do. Simulators also give you much better visibility. You can record as many signals as you want in your simulation, right? The problem with simulators is they cannot model asynchronous interactions easily. There are ways of doing it, right, or accurately. So for example, if there are timing related errors that are happening in your program, it becomes very difficult to catch them through simulators, because simulators have sort of predictable and repeatable behavior which may not be exactly what you want in order to catch the bug. There are debuggers that actually involve hardware in the loop. What that means is, they allow you to literally single step through each assembly language instruction in your code, or it could be through the lines of code that you have written in a language like C, right? So you can actually say, okay, go forward to this particular line and then stop. GDB is an example that we have already looked at in the context of C programming, and similar kinds of things can be done where you can directly run GDB with a connection to a piece of external hardware and use its connectivity in order to actually step through the code that's running on that external hardware. There are a number of other things such as trace buffers, logic analyzers, and so on. In other words, a lot of different tools that are available to help with debugging and to identify problems with programs. This is a very complex but important part of system level design, and is something that we will be looking at in a little bit more detail at a later point.